Okay, I think we're live. I'm going to give it a second or two for people to join, but in the meantime, I thought I'd flip through some generated robots. This is from the book 1,000 Robots by Ben Barry, using OpenAI's DALL-E 2. But yeah, just a very pleasing collection of images and something to look at while we wait for people to join. Because this is a more sort of interactive, casual stream rather than a formal lesson, I am keen to try and get as much engagement as possible. Unfortunately, our most discursive student couldn't make it. He will be missed, but yeah, we'll see if we can get some discussion going, and if you've got questions or things you'd like more info on, you know, could you dwell on that, explain that a bit more, we can definitely do that. And we'll also probably hang out in the Discord afterwards for some even less formal discussion, just hang out in a voice channel. That is if there's anyone interested. So I'm going to try and check on Twitch, see if there's anybody here yet. Nope, so we're going to look at some robots until, maybe one person. Great, okay, so I guess this will also be recorded, so there'll be that info out there for other people. Hey Ollie, great to have you. Excellent. All right, well, let's dive in with a sort of rough outline or plan of what we're going to do today, besides just look at some pretty robot paintings. So I thought it would be worth just going through a couple of things from recent news. First off, a place to keep track of what's happening in the news. Yeah, go through a couple of papers, just take a sort of high-level overview using some of the tools that we've got from previous lessons, and just getting a kind of understanding of what's going on, what are the improvements that they're suggesting. And then based on something that I said right at the end of last week's lesson, I kind of got super sidetracked away from working on a new lesson into exploring some ideas around latent diffusion and, in fact, latent denoising diffusion GANs, which I'm going to missay a number of times today. So we'll look at that paper, and then we'll look at the project that I did kind of exploring those ideas, just as a bit of a show and tell, and something that I didn't have time to dive into last week, but wanted to cover while it's all still fresh. It's also an ongoing project, so this will be the start of something, and I'm hoping to build out the information around it. But yeah, just give a little brief overview of that. Excellent, so I see we've got a couple more people joined. Wonderful, welcome. So first up on the agenda, the first resource I shared in the Discord, which before I forget, I'm going to share in Twitch as well, just so that everyone's got the links handy. So this is a question that kind of just addresses more like how the heck do you stay on top of what's going on? And one of the best resources is, I believe, actually someone who's took our own course, but now also runs multimodal art, and I think actually ran it way before this course existed. So we can't claim any actual credit, but Apollonia, don't know how to pronounce the name, but really cool dude. There's a video interview if you're keen to like see the person behind it. But this is just a great source of keeping track of what's coming out. The sort of newsletter every week aggregates a lot of the stuff that's happening. So this is just another person to add to your list of Twitter followers and so on. And also a great kind of improvement in interface for a lot of these models. This Mind's Eye is really fun. Highly recommend having a play. But yeah, just wanted to shout that out there as a good source of sort of staying current, especially with this news section. There's also lots of other people on Twitter worth following, and I think a lot of them are linked here. But I found these updates kind of a really good broad coverage of all the things that seem to be going on. So that's item number one. Done. Hopefully, if the other two are as quick, this will be a very short stream. Okay, so item number two, I think this had come out just before last week's lesson, being sort of announced and publicized, but we didn't really talk about it much because the topic was more relevant to lesson 6, where we talked about modeling images as sequences of tokens, working with transformers. So I thought it would be fun just to, in sort of 5 minutes, unless anyone has deeper questions, just have a read through of this paper and see how they really implement a couple of super smart ideas that are going to become, I think, more commonplace in other places. And so I'm really looking forward to the release of this model. But more than that, I think just it's a great kind of template for future work in the same vein. So you've got to start out with a grid of really good looking outputs. these are some demos from their pipeline. And so this paper presents a couple of things. One, they show their sort of core model, right? This cross-modal general language model, COG-LM. And then they combine that in a sort of pipeline for generating images. So if you remember our lesson 6, I don't have the notebook open, but we modeled an image as a sequence of tokens, and those tokens were the codes produced by a quantized autoencoder like VQGAN. And then we said, well, we can treat this just like a sequence of text, and we can use a lot of the learnings from language models to auto-aggressively predict the next token in the sequence. And in doing that, we're learning a whole lot about how images are made and so on. So that's great. And this paper kind of takes that idea and scales it up and runs with it and does all sorts of tricks to build on that. So the reason they're pursuing this approach, even though diffusion models seem to be kind of the vogue, is like, well, actually, these transformer models are still good, and there's issues with all of the current systems, right? Some of them are pretty slow. Some of them take a lot of time to train, and especially transformer-based models when you've got long sequences, memory scales. Diffusion-based models, when you've got large images, the computation can be quite tricky. They highlight a problem with models like the one that we built in lesson 6, is that they're treating this as a sequence and they're going forward in the sequence auto-regressively. And so they call this out as a potential bug, right? If you're generating something in the top of an image, you can't, incorporate information from later in the image, which is a problem when you're trying to do things like inpainting. And so they build on that and they say, well, we're going to do a couple of things. One, to keep the computation small, we're going to work at quite a small scale initially, right? And I think they have 20 by 20 tokens. So their sequence length is only 400 plus whatever the text is. Whereas if you look at something like the original DALI paper, I believe that was something like 32 by 32 tokens. And if you try and scale that up to higher resolutions, you can see how the amount of the sequence length grows kind of quadratically with image size. And so the amount of memory required and so on also grows quadratically. And so you just end up with this really nasty scaling. So they say we're going to keep it small first. We're going to generate a whole batch of images using our approach, their multimodal language model. They're going to filter the samples. Again, using that same model in a clever way. And then they're going to upscale them with this like direct super resolution. And we've seen attempts at this with various systems, but the problem is you tend to scale up the artifacts as well. I know from my experiments trying to fix VQGAN artifacts, it's a little bit of a tricky problem. So then they come up with this third technique, which is kind of iterative super resolution, where they erase a lot of the parts of the image and refill them in anew. And it turns out this, this gives a nice kind of consistency to the final high resolution images. So really, really neat approach. Let's just have a look very briefly at how they're doing it. So a lot of this looks fairly similar to an architecture like DALI or like any of the taming transformers stuff we've looked at. We have our input text being tokenized and going into a sequence. We have our image being tokenized again with a VQVAE or a VQGAN and going into that same sequence. So we have this kind of one unified sequence. But unlike ones where we just learn sort of in this unidirectional mode, they treat this as a masked language modeling task, right? So they're going to arbitrarily mask out some image tokens, some text tokens. And so they have this like single thing, which is just basically fill in the blanks. We're going to give a sequence, we're going to hide some of the sequence and ask the model to fill that in. And the neat thing with this is that by changing how you do this masking, you're changing what the task is. If you give it all of the text tokens and none of the image tokens, then you're training a text to image model. If you give it most of the tokens but erase a couple of image tokens, then you're training infilling or image correction. If you mask out all the text and you present just the image, then you're training it to do image captioning. And so this one single model, depending on how you mask out your sequence, is actually learning multiple different tasks. So this pre-training task of filling in the masked regions, it turns out is very, very useful for then these various different downstream tasks. And so that's great because then they can now do this fine-tuning where they're doing this masked language modeling on these sequences. They can do that a whole lot and train a really big model. And then when they want an image captioning model, they just fine-tune it on that specific task. When they want an image super resolution, they fine tune it on that. And that's, in their case, super resolution means erasing a lot of the tokens and refilling them in. And when they want text to image, they've got text to image. So really, really clever architecture. And it works incredibly well. So I think the paper shows some examples of like how it generates. Now, there still would be an issue in that a lot of these models can kind of just still process the token up into a point. So a lot of the rest of the paper is refinements around, let's see, this kind of like ability to do multiple parts in parallel here, these local windows and so on. And so to do that, they have their special local attention mechanism and various other sort of CUDA optimizations and so on. Basically just saying we don't want to have to deal with the whole sequence about the whole image just to classify the next token in one small part. And so a lot of this paper is also just outlining some really smart optimizations. So yeah, again, things that I think will be useful beyond just the specific paper. A lot of these ideas could really help speed up any sort of transformer text to image or multimodal transformer works in the future. So I don't think I've got too much more to say on this here. They've got some neat little information on exactly how they do the generation. Their code is at the moment not really out, but they promise it's going to come out soon, right? So they say code and demo will be updated here. At the moment, there's a web-based demo that's in Chinese, but you can Google Translate and try it out. I think it might still be their older model, but all of that's coming soon. And when it does come, you'll hopefully have a bit of an understanding of why it's cool. And if these images are not too cherry-picked and actually are representative, we might have a great open source text-to-image model on our hands that isn't a diffusion model. So that'd be great. Yet another one to add to the arsenal. Okay, if you've got questions on that, you can chuck them in the chat. Otherwise, we're going to move on to the next paper. So I'll keep an eye on the chat. We'll start talking about the next one. But before I get too deep in, we might backtrack and answer anything more about CogView. Otherwise, we can also discuss this in the lounge afterwards. Okay, so that's that one. Oliwag asks, does it mention the dataset that's used and how it was scraped? So they have, I think it's something like 600 million, so similar to the size of DALL-E. Maybe, no, it's less. That's right. So they have maybe not even 100 million images, and it's combined Chinese, English, and then they call it like the three languages they talk about, Chinese, English, and image. The three different sort of types of token that they work with. Let's see if I can find, just really quick, here we go. So pre-training on only 30 million text image pairs. And then they have some that they filter out, and then they use, some subset of that for the different tasks. So really small data set. And actually that's incredibly promising because now that they've put this out here, and hopefully once they release training code and so on, there's nothing stopping a big group with lots of compute from coming along and recreating this on a much larger data set. So yeah, that actually means that these results are especially impressive, because if they can do this with 30 million pairs, imagine Lion 400 million, or even the larger Lion 6B, that's 6 billion image caption pairs. Another question, great, this is great guys, I love the interaction. Are they masking every possible combination? That is, if sequence length is n, total combinations. No, so as far as I know, they, at different stages in training, they have different like masking regimes. I know in the fine tuning especially, they kind of focus on one task. So they'll just mask out all of the text or most of the text, ditto all of the image. Yeah, so I'm not entirely sure exactly how they structure that, but I think they have like specific strategies. And I know for the upscaling like artifact correction, so they then train it quite a bit on situations like this, where they've masked out, say, 2/3 or 75% of the image tokens, and they're trying to fill those in. And they have some great maths as to how exactly they figured out the ratios and so on. I didn't read the paper too thoroughly, but yeah, so I think I don't think they do every possible combination. For a given image, they probably apply a random mask, and then however many epochs in the training, it'll be a different mask each time. But they're definitely not doing 30 million times all the different possible mask binary masks that you could apply to a sequence of that length. I think that would be way too much training. Cool. All right. Yeah, I guess further questions we can always come back to or talk about after the actual stream ends. So the next paper is something that I sprinkled in at the end of lesson 7. Let's actually go down to where I mention it here. So we talked about, diffusion, we talked about sampling tricks, conditioning, getting fancy with classifier guidance and so on. This whole idea of latent diffusion, kind of just right at the end, explained the idea behind that. Klube condition latent diffusion, and then in this kind of final section, which I was writing, the afternoon of, this field is evolving really rapidly, and there's continually new stuff going on. And I just linked to this thing that I'd just seen and taken a quick look at. And so today we're going to try and do that a bit more justice, because I think it's actually a really cool paper. At the time, I wasn't sure whether it was just a GAN in disguise, but we're going to look at this tackling the generative learning trilemma with denoising diffusion GANs. So this is the link to the archive page, and you can get to the PDF from there. And so first of all, what is this trilemma that they talk about? Well, we've seen various generative models, right? And they all tend to do some things really well and some things fairly poorly. So something like a GAN, really fast to sample from a GAN because it's usually just one pass through a network and it spits out a nice image. They can also be quite high quality, but they don't necessarily do a wide variety of outputs. So you have this thing called mode collapse. You can't guarantee that your GAN is going to be generating the same variety as the original data, but it's fast and it's high quality. Then diffusion models, they're sort of in the news and popular because they do cover a lot more of your sort of data set variety you get from these diffusion models. They have really good coverage, and the samples are really high quality, like we've seen, sort of state-of-the-art quality in the case of Glide and DALI and so on. But they're slow. We mentioned that we have this iterative sampling, which can be order of thousands of steps, and even with fancy refinements and new sort of advanced sampling techniques, it's still 25, 50 steps, each of those steps being a full pass through the model. And so they're not necessarily high speed. Some could argue they're getting there with these different sampling techniques, but they're still a little bit slow. And then if you want to get fast sampling and mode coverage, you can look at things like variational autoencoders and so on. But then your generated samples aren't necessarily high quality. So this is the sort of trade-offs that everyone's working with. Everyone's trying to find their sort of key here. And if you look at something like these transformer-based models, they can generate quite high quality samples. They can cover a lot of the data. Their sampling is sort of fast, but they do have to do multiple steps through to generate a full, sequence output. Yeah, so everyone's kind of doing these trade-offs. And in this paper, they try and find something that combines all these together. So that's their sort of sales pitch. I think it's quite a nice way of framing the problem. And they're going to try and say, how do we adapt this diffusion process into something that can be much faster? So that's the goal of the paper. We'll give a quick summary, and then we'll look at some code to kind of explore this practically. In fact, what I'm going to do is open the notebook that I shared and just go runtime run all, and you'll actually have to restart after the requirements install, but I just want to get this process going so that we're not waiting for it once we come to look at the code. Okay, so this is this denoising diffusion GANs. So what's their key idea here? How are they going to do this? So they give some background on diffusion, right? We have this situation where we're gradually adding noise again and again and again. And in diffusion models, this is done thousands of times. And underlying the idea in diffusion models, one of the sort of key insights is that if your individual steps are small enough and you do enough steps, then you can make assumptions about the distribution of the noise and the denoising step. Specifically, you can prove that it's very close to a Gaussian distribution. But if you have too few steps or your noise is too large, you're doing too much in a single step, that assumption no longer holds. And so this, denoising diffusion GANs, they say one of the things we'd like to do if we want to do larger steps is break away from this assumption. We'd like to be able to not just have a sort of single mode Gaussian distribution assumption. We'd instead like to have a multimodal distribution that our model can generate. And so they want to be able to take larger steps, and to do that they need a model that's breaking from some of these simplifying assumptions made in the original paper. And to do this, one of the ways you can think of that is that they're going to take their Q from something like an actual GAN, and they're going to take in this latent Z, right? So some extra latent noise separate to the noisy image. And this is going to mean that instead of given a noisy image always producing the same predictions, they're now going to have this extra randomness, this extra ability to generate a distribution of predictions rather than a single prediction by taking in this random Z. And so that's going to give them a more powerful generative capacity and variety. And that hopefully means that we can now jump larger steps. So that's sort of one of the key insights here in this generator. In terms of training, they also say, well, we're going to change in diffusion. We were just caring about learning this reverse step, right? This p theta, undoing a single noise step, and that's going to be our sort of target. And so given a noisy image xt, we know the noise, we're going to try and predict that. We can calculate the mean squared error. So the loss function was fairly simple, right? When we came to time to actually train, our optimization loop was really small and concise. So the gradients, get some images, sample from t, pick some random time steps, find the noisy images, predict the noise given those images, and then mean squared error loss between the predicted noise and the actual noise. Very, very simple, very concise, single loss function. So the fact that we're now trying to learn not just the small, easy, sort of very minute denoising step, but a much larger step, they say, okay, well now to kind of stabilize this and to try and like guide it in the way we want, we're going to introduce something that looks very much like GAN training, right? Where we have our generator network, it's going to produce some prediction, but then we're going to evaluate that prediction with a second network, the discriminator. And so just like in any other GAN training, these two are hopefully going to be getting better sort of antagonistically. The generator tries to fool the discriminator tries to tell the difference between real and fake. And in this case, it's not real and fake outputs, but given an input, right, noisy image x of t, we're going to use the generator to predict all the way to the output, x0, and then we're going to renoise that back down to t minus 1, right? So it's kind of doing this step from x of t to x of t minus 1, but it's doing that by always generating x0 and then noising that back with this posterior sampling, just like we would if we were generating this from training data. And then the discriminator is going to try and tell whether this or this is a more plausible denoised version of this noisy input. So I hope that's making sense. I really hope you can see my mouse pointer, otherwise I'm just talking about this and this without much grounding. But yeah, so it's a pretty interesting formulation. You might say, why not just train it to go from a noisy input to the output and just look at the outputs and do the whole thing in a single step, and then wait, isn't that a GAN? But they talk about in the paper quite convincingly that no, actually having it still be several steps, and when I say several, I think their number of steps is like from 4 to 8, some really low number of steps, but having it be this stepwise process, it just helps smooth the distribution, it helps it learn better, and it really is a different process to just training a GAN. And so they have a little bit more background and info on that. But I think, yeah, there we go. Thanks for the confirmation that you can see what's going on and that I'm not just talking nonsense. Yeah, so I think this is kind of enough of an overview to say, okay, this is pretty neat. We're training much fewer steps. We're training with a different objective. Right now we're going to train our generator to, given any input x of t, taking in z as well and conditioned on t, produce a plausible x0 that when it's renoised fools the discriminator. And so that's our sort of training objective. And this is kind of all the reading I did before I said, okay, I'm going to try and do this myself. And so the final part of this live stream is going to be just looking at taking this kind of hand-wavy first skim of the paper. Can we actually get some results from this? So if you want to look through the rest of the paper, they've got info on the results. They've got info on, the explorations that they did. They've got some experiments to try and see how well this covers different modes. They also have a whole rationale section of how they chose their variance schedule, which I just completely ignored, but we'll see if it works anyway. So if you do want to follow along, the Klube conditioned latent denoising diffusion GAN demo notebook has been shared in the Twitch chat and the Discord, and we're going to try and train our own model, and we're going to talk about all the additions I've made to this paper, because for this demo I just wanted one demo that's going to incorporate all of these cool ideas into one. So you're welcome to follow along with me. The training itself will take like 15 minutes, so we're definitely going to stop that early. But if you do want to take this notebook, run it for longer, experiment, you can. There's also a script that I share here. If you want like a more fleshed out version of what this notebook is doing that already has weights and biases logging and tracking and some extra features as well, you can check that out, and you can see what an example run looks like, where you've got examples as it goes, live plots, etc. But for the notebook, it's fun to just run it ourselves. Okay, so let's see what our objective is here, and then let's talk about the additions. No, let's do that in the other order. Let's talk about the extras that I sprinkled on here, and then let's look at the training loop. So if we go back to our paper that we're trying to reproduce, so this is what we kind of trying to achieve here. We're going to take a noisy image, and we're going to try and predict the denoise step by actually predicting the image itself and then renoising it, feeding that to the discriminator. Now there's some extra things that I mentioned in lesson 7 as kind of ways that we can extend the capabilities of diffusion models, and I wanted to take a few of those same ideas and apply them. Well, can we use them to extend the capabilities of this denoising diffusion GAN? And so number one was to say, dealing with images, right? These images are made up of lots of pixels, 128 pixels by 128 pixels by 3 channels. That's a lot of data. And so the first sort of modification that's becoming popular is to say, well, why don't we do this in the latent space of an autoencoder? And this just means that we now have a much more compressed representation of our image. And if we can apply the diffusion or the denoising diffusion GAN or whatever, apply our processing in this latent space, it's much more computationally efficient. And then at the end, we just decode back into an image. So that's something we're going to try. We're going to work with an autoencoder. And then the other one was saying, what if we condition on some extra information like text, right? And so just like, DALL-E 2 or whatever, here's DALL-E 2 generating some robots. If they can do it, why can't we? We'd like to, give our generator not just the noisy image Z and T, but also something else to help it along, which could be like a caption. And then I said, well, Klube comes along, and Klube gives us a representation of some text, which we can use as conditioning. And we can also get a representation of an image, and actually the representation of images and text with Klube look very similar. And so we can use either. So if we can condition this on a Klube embedding, then it means that at come time to generate a new sample from completely random noise, we could say, okay, here's an image I'd like you to denoise, but it's all just noise. And here's some extra information to help you, and that's our conditioning. And if we can feed in conditioning based on text, then hopefully we can generate an image that seems to match that text. So those are our two sort of bolt-on additions to this diffusion denoising GAN. We want to use Klube, and here's a little demo of that in action. We're going to download a pre-trained model, and then we can take either text or an image, right? This is just a sort of fake image, but we can show how they both map to the same sort of space, and this is going to be fed into our network as just extra conditioning information for it to use. And so while that loads, we can, I guess, look at the code for the next part. So the other component of this is an autoencoder. The one I've chosen to use is from the Latent Diffusion project by Comfers. I think that might be the first sort of application of latent diffusion, and they train some really neat autoencoders specifically for that task. So this one is going to take an image and it's going to reduce it quite substantially. And so we'll see once we run this code Sorry, it's just taking a little second to download the models. We'll see once we run this that our original image, which is 3 channels, 256 by 256, which might be really large if we want to work with a number of them in a batch. We're going to take that and we're going to shrink that down to a much smaller representation of 32 by 32 by 4. So our latent representation is going to be a much more reduced version of this big batch of images. So those are our 2 pre-trained models, both really great models, both freely available, open source, code is open, etc. And you can go and check out the respective Git repositories and things. I think this one comes from Catherine Crawson's Gloob training repository, and this one comes from CompViz's latent diffusion repository. And if you scroll up to the top where I install the dependencies, you can get the GitHub links. Okay, so these are our 2 modifications. We can take an image, we can encode it into this latent representation, which is much smaller, and then work there and decode it back to an image when we're ready. And we can take an image or text, and we can shrink it down to this 512 dimensional Gloob embedding, which we think will be useful for extra conditioning. Okay, so that's that out the way. Next, we need some data. So for this, I'm going to use a dataset of faces, quite a popular GAN dataset for whatever reason. Shouldn't take too long to download on Colab, but again, yeah, we can chat while that goes. If you've got any questions on, what we're trying to achieve here, if you've joined late, feel free to chuck them in. In the meantime, I'll also check Discord to make sure I'm not missing anything there. Oh, cool, we have a question there. Could you elaborate a bit more on what mode collapse looks like? Cool. So mode collapse is when you're training a GAN. Let's look at this picture, although this is not an ideal picture here. Forget about the noisiness and the T and so on. Our GAN, actually, even better picture is up here. The objective of the generator part is to fool the discriminator, right? So this generator is trying to generate an image that the discriminator thinks looks real. The discriminator is seeing real images and fake images and try to learn the difference. And so to do this, one thing the generator could do is just generate a whole variety of very plausible looking images, and that's of course what we want. But what it can also do is say, well, there may be hundreds of types of data in this data set, but if I can generate a plausible looking face, and the discriminator sees some faces, some dogs, some cats, and then it sees my faces, it might not be able to tell those apart as fake, right? So we can fool the discriminator, but we can fool it with 1 or 2 or 5 or 10, a limited number of examples that don't necessarily represent the full data set. And you can see I don't know if they do it in this paper. In some papers, what they'll do is they'll say, let's compare our results to those results that come from a GAN. Maybe they do it here. Yeah, and what you'll see if you look at enough outputs from a GAN is that there's sometimes like particular patterns that they fall into, or all the ostriches are just an ostrich's head. Whereas if it's got better mode coverage, you might see a whole ostrich, an ostrich's head, some ostrich's feathers, a much larger variety. So that's mode coverage hand waved away. But yeah, the idea is we want to generate as high a variety of data as possible while still fooling some discriminator or while still having high quality samples. And one of the things that they'll show here is that not only do they produce really pretty looking, faces, they can also produce a wide variety, and they have a good coverage of the types of ones represented in the data. So that's our goal. We want to have something that can generate a nice wide variety of outputs as well as just good quality outputs. Okay, so our data is done downloading. Each of these has an image and a caption, although in this case, the caption for all of them is a photo of a face. And I put that caption in myself just to match with the format of some other data sets I was using. So that in itself is not particularly useful to us, but we'll see that with Gloob, we can say, well, why don't I just use the Gloob embedding of the image, and hopefully it can still learn something from that. Okay, so that's our setup. We've got our building blocks, right? Gloob for conditioning, autoencoder for shrinking down into the latent space and back, and we've got our data. So now we can make the actual model. And there's going to be 2 components here. There's going to be the generator, which has to take in an image and output an image effectively, or in this case, take in a latent and output a latent. Either way, we're going to use that unit architecture that we introduced in AIAIART Lesson 7, so last week. Here we go. We're going to use something that looks like this with a few extra bells and whistles. And so this is our generator, right? It takes in our noisy image x of t, and it takes in conditioning information, and it takes in a z, and it spits out a prediction. For the discriminator, we're actually going to copy and paste this UNet, pretty much, but we don't need to produce an output image, we just need to produce a true or false prediction. So we're going to take just kind of the left-hand side of this down to the middle. We're still going to take in some inputs, right? We're going to condition on the previous image, condition on t, condition on, and then take in an image and output a prediction for real or fake. So what I've done here is we can just create these models with a single line. But if you want to see the actual code behind that, it's very similar to the code from Lesson 7, but it's just been wrapped up in a nice, neat sort of library, effectively. And I can talk a little bit more about what this is, how I built, this thing that gets this nice, documentation site and so on. But if you're interested, you can go and see the kind of docs, auto-generated docs, or you can click and see the actual source code on GitHub that's going to define, this is what our unit actually looks like. We have some parameters, it's going to set our number of layers and so on, the downward path, the middle, and then the upward half of the network. And in our forward pass, we're going to take in X, right, our noisy image or latent, T, our Klube embedding, some Z, right, that latent input that I talked about that turns this into more of a GAN. And then we're going to, cluster together our conditioning information. We're going to get our image in. We're going to feed it through the first half of the network, the middle, the second half, and all the time we're going to be adding in our extra conditioning, and then we're going to produce our output. So you can go and dig into that code further. I'll also talk a little bit later about how I polished it up and tidied it so that I can make these experiments easier. But for our purposes now, it's just good enough to know we have a model that's been defined somewhere, and it's going to do this kind of task that we want as long as we train it well. Okay, final step, setting up the actual diffusion part, right? Doing the noising and the denoising. That's again just wrapped into a little class that you can check out. It's also up here, this context. It's just, again, wrapping up those functions for, for the forward sort of noising operations and so on, just abstracting that away from this notebook. But we can see how it's working in practice. We can still do those same operations that we saw in Lesson 7, right? But now instead of taking an image and applying noise, we're going to take our image, we're going to encode it with our autoencoder, and then we're going to do our noising. And only when we want to view it do we then decode it back into an image. So it's still very similar to the diffusion stuff from last week, but now it's happening in the latent space. And the idea, again, is just to reduce the amount of compute and increase the amount of images we can process by having this more compressed representation. Okay, so we actually going on a little long. That was maybe too much information, who knows? You can give me feedback in the chat if you want more or less. But with that, we could then actually, we can run the training, but I'll just show what the outputs look like. Oh, we can't even. And I didn't bother to make a copy of the notebook before I ran, so anyone who has it, you're also going to have this in progress version. Really sorry about that. Anyway, okay, well, we can wait 15 minutes while this trains, maybe less. I might stop it early and let's reduce the number of batches. We're not going to get very good outputs, but we'll get something, and we can we can explore it from there. So I'm just going to run from the data loading again, train it for only 100 batches, and then run these little examples. Once this lesson is over, or this live stream is over, I'll rerun this with a larger number. But in the meantime, we can also look at a weights and biases run to see kind of what's happening here. Oh, and actually we should look at our training loop since we've talked so much about that. So you can see this is a lot more code than the training loop for our diffusion model from Lesson 7. And that's because we're no longer just optimizing the difference between the predictions and the target. Instead, we have this whole trying to fool the discriminator business. And so in our training loop, what we're going to do is we're going to take a batch of images, we're going to noise them to x of t, we're going to produce a prediction with our generator, we're going to noise that to x of t minus 1, and then we're going to, first of all, update our discriminator, right? We're going to feed in the true images and penalize it if it doesn't predict them as true. We're going to feed in our fake images and penalize it if it doesn't predict them as fake. And then we're going to take how well we fooled the discriminator. We're going to use that to update our generator. And then if we want, we can also look at the output and update the generator based on that. So there's a number of steps here. But if you've done any sort of GAN training before, right, this is the PyTorch GAN tutorial, you'll see it's the same sort of process for a lot of GANs. You have, let's scroll down here. In our training loop, when we come to training, we're going to first of all train the discriminator by calculating the loss, doing a backwards pass, passing through the fake samples, doing another backwards pass, then training the generator. And so it's the same sort of idea. And so when we look in our demo that we're doing currently, we're going to get a batch of images. We're going to zero everything out, prepare for our run. We're going to encode those images into the latent space. We're going to get a random t and a random z. We're going to get our klub embeddings, since we use that as conditioning. We'll zero those out some of the time. We're going to get our noisy versions of the image. And then we're going to feed through the true images, the real images, through the discriminator and update it based on that. We're going to generate a fake batch of noisy images or latents, and we're going to update the discriminator on that. And then we're going to train the generator. So we're going to now switch over to training UNet rather than the discriminator. We're again going to say what was our predictions from the discriminator on our fake batch. We're going to use that to update our generator somewhere. I might be missing a line that says, oh, here we go. There we go. Yeah, we're going to do the backward pass. Couldn't see my code. And then we're also going to calculate our reconstruction loss. This is kind of optional, but it just helps stabilize training. And so if all has gone well, we're getting better and better at the core task of producing images. We can see initially our discriminator doesn't know how to distinguish, but over time it starts predicting closer and closer to 1 for the real images and closer to 0 for the fake images. But it's not perfect. In other words, we're still fooling the discriminator some of the time. And if we look at a full run on weights and biases, you'll see something similar, right? Our reconstruction loss gets better and better and better. And our generator, right, these fake images are still sort of distinguishable as fake to the discriminator, but not perfectly, right? If it was perfect, these would be down at 0, and the predictions for the real images would be 1. But as it is, they both tend towards some sort of center. And so that shows that, okay, it's doing well and it's generating, somewhat plausible samples, depending on your definition. Okay, so this is still trained on a few minutes rather than hours, but it seems to be doing something. Okay, if this had worked, we would see some variety here in these generations. And excitingly, that would be based on our text prompts. So again, let's switch over to, I think I have some examples open. Let's see here. So the text prompts used for this was a photo of a man, I think, or a male face, a female face, a mugshot, a photo of a face, and a man with a beard. And you have to use a little bit of imagination, but I can kind of see a bit of beard down at the bottom right here. And there's definitely something different about the images. I'll let you do your gender assumptions. It's definitely not obvious. But the cool thing is this model wasn't trained with any text that described any of those attributes. All we had was the conditioning from klub, and yet somehow it's able to generate something. If you say the color blue, it even looks kind of bluish. So yeah, maybe it does need a little bit more than 2 minutes of training. But I thought it was a cool demo. And it shows that, these are pretty powerful components. When you plug them all together, we have now a diffusion-like generator, but that it generates images in 4 steps, 8 steps rather than 1,000. And it's able to be conditioned on text or images. And during training, we can condition entirely on images, but because of Klube and the way that it maps both images and text to the same sort of space, come inference time when we'd like to generate, we can feed in a description, and we can hopefully get something that looks kind of like that description. So I thought that was pretty neat. I'm sure I've skimmed over things a little bit too fast, so if you've got questions on how the heck this is working, like how does it do the text part, what is this reconstruction, we can chat about that. So do put them in the chat. But in the meantime, can this do more than faces? So rather than our 1 minute training on faces, what happens if we scale this up? And so that's kind of what I've been playing with this week. And yeah, I haven't been able to do too much training yet. But if we want to look at this run here, which I guess I can share, no, I'll just show the demos. So for this run, instead of training on a few thousand faces, I trained on a dataset called conceptual captions, which is something like, millions of images with captions. And we generate some examples. And so obviously these are not perfect images, but the descriptions for these were, let me get my little note, a photograph of a face, I think, an underwater submarine, a red stop sign, green hills beneath a blue sky, a group of people, an armchair in the shape of an avocado, and blue ocean waves. And so, unsurprisingly, this doesn't generate a flawless avocado armchair like OpenAI's model does. But there's some green in there. Green hills beneath a blue sky. With a bit of imagination, you can believe that that's what's going on there. It maybe hasn't learned what a stop sign is, but it definitely knows what red is. Blue ocean waves, likewise, I could believe some of these were from an ocean picture or on a beach. And I think in the Discord, which I'll bring up now, I shared a few additional examples. So let me just pull this up. Here we go. Yeah, so these are more examples. Watercolor painting of a rose. You can squint and imagine that. Blue waves on the rocks, lush vegetation. So to me, this is pretty cool. During training of this larger model, some of the time I would feed the Klube embedding of the caption because I have that information. A lot of the time I just embed the image. And we train in the same sort of way. Again, it's all in the latent space, so we get this weird artifacts from decoding sometimes. But it's pretty cool that in literally 2 hours on a single GPU, albeit a big GPU, we're able to get something that shows just a hint that it's able to take in a description and produce an image. So to me, that's really exciting. I can't wait to see what real well-done implementations of this code look like compared to my hacked together versions. I'm going to keep experimenting with maybe trying different autoencoders or just doing the Klube conditioned diffusion denoising GAN on images themselves rather than the latents. But yeah, I just thought it was basically fun enough to be worth doing a little live stream, talking about it more, seeing what of that explanation doesn't make sense. Yeah, so we'll talk about that. I see some questions, which is excellent. Thanks for those. So precisely Felix says, would it be possible to generate with an input image and an input text, or can it only be one? So that's a great question. The way I've set it up, it takes a single Klube embedding as your conditioning information. But the nice thing with these sort of conceptual spaces like the latent space of Klube is that the sort of meanings are kind of aligned, or ideas are kind of aligned. And so what I mean by that is that if you take 4 pictures of dogs, they would all map to certain positions in that space. And if you kind of averaged those, you would probably still have something that represented doggishness. And so if you now have an image and a text, and you took the Klube embedding of the image and the Klube embedding of the text, and you took the average of those two, my guess is you would still get something that kind of captures a bit of the essence of both of those things. So I haven't tested this thoroughly at all, but my intuition is that you could definitely use maybe multiple texts or images and texts, and you could vary how close you go to each of those in the Klube embedding space and generate with those and see what it does. So yeah, in theory at least, you could feed in a sort of combined or average Klube embedding and hope that it captures the essence of whatever inputs you fed in there. Latent XVF asks, how long did it take to train on conceptual captions on which GPU? So let's talk about that just a little bit. So I was on Paperspace because I had a little bit of credit given to me, and you can rent GPUs by the hour there. Sorry, let's go there. So it was on an A100 GPU for that particular run, just because I was in a rush. I wanted to do something this morning before I went out shopping and Mother's Day events and so on. And so that's a GPU with, I think, 40 gigabytes of VRAM and a lot of compute. It's a lot more powerful than something like, like a sort of Colab GPU, for example. But if you look at that, so let's just select the right runtime. I think the price is something like $3 an hour. So I'll scroll down. Yeah, A100 GPU, $3.09 an hour. So that's what I used. And on the machine that I ran, I think I ran it for 3.5 hours. So call it $10 of compute, which is not bad, especially because I've got, like I said, a little bit of credit. And the way I trained it on conceptual captions, which it's in itself is a large data set, the way that I set up that data set, and by the way, this is documented as well on the GitHub site, is to use the streaming functionality of web data sets. So here's the, here's the conceptual captions kind of data loader code. So we specify our URLs, right? This has been uploaded by the Lion kind of collective, and they have the data set split into 1,200 different tar files, or actually I think slightly more than that. I just arbitrarily, I knew it was 12 million images. Each tar file has like 10,000 images. So we can specify that URL to web data sets, and then we are not going to download the images first. Just as they're needed, they're going to be streamed from that URL into the data set and then processed. So it's a pretty neat setup. It means that you can run this code and see some images almost straight away. And behind the scenes, it's using a number of workers, little sub-processors that are constantly making sure that they have the next batch ready, and they're pulling down that data as needed. So in this case, I only used the first million or so images because I said, train for 2 hours or whatever. And yeah, this is streaming that in. Because it's a data loader, they do this nice thing where when you request one batch, they already have the next batch ready to go. And then as soon as you've taken your batch, they start processing the one after, so that there's always kind of one in the queue. And what it means is that when you look at this run here, even though we're streaming the data, if you check at the system metrics, you'll see that the GPU utilization was up there really, really high, because it's not spending much time waiting for the data. The data's already been pre-processed, converted into a tensor, sitting there ready to go, so that as soon as it's ready, it gets loaded onto the GPU and we train. And you can see the network traffic here scales up to quite a large number. That's because over the time we're downloading, over 1 million images, but the GPU from the get-go is going brrr. So very, very satisfying to have set this up. The other reason it could go this fast is that normally training on 1 million images, say they were large images, 256 pixels by 256 pixels, you could probably fit 32 or maybe, probably 32 images in a batch on an A100, fewer on a smaller GPU. But because we're using our autoencoder, we now have, for a 128 or 256 pixel image, we now have a 16 by 16 by 4 or a 32 by 32 by 4 latent. And so where before you could only fit 30 or best case scenario, 60 images in a batch, because we're encoding them to the latent space, we can now fit, I think my batch size here was, let's double check, batch size, this was a small batch size for this. In other experiments with a smaller network, so less memory requirements, I was able to fit like over 1,000 images in a batch. I didn't find that was particularly productive, but it was possible because our representations are highly compressed and we're working in this latent space. Yeah, I hope that makes sense and answers the question. I can see myself time delayed by about 15 seconds, so it's a little tricky to get real-time feedback with this system, but yeah, I'll keep an eye on the Twitch chat and the Discord. I've kind of been neglecting the Discord, but oh, we have another question in there. So we have a question in the Discord about this illustration right at the top of lesson 7 that's asking about the notation here with this little z. And so, yeah, we have this feed in noise and turn it into an image is kind of the general formulation of generative models, right? Turning images into noise is easy, turning noise into images, that's generative modeling, is a quote from, I think, the author of that blog post. And so in a GAN, we feed in random noise, we get an image out. In a autoencoder, during training, this Z is not random noise, right? It's just our latent space. But when we now want to generate fresh images without any inputs, we just feed in random noise. Ditto flow-based models. And so in diffusion models, when we start with an image and we apply a lot of noise, we get something that looks almost random. It's not, completely, but it's very, very close mathematically. And when we want to generate, we do start with random noise. So for consistency here, yeah, that's what this is. This is our random noise image, and then we're going to gradually denoise that and denoise that and denoise that until it looks like a plausible output image. Where that differs from this formulation is that now, in addition to potentially starting with completely random noise as the image, we also have this extra Z, which is some other dimensional latent that we feed into the generator part of this GAN. So I know that's a bit confusing, the notation wise. We could also call the starting image Z as well. And you could say like Z1 and Z2. They're both, during generation, we feed in random noise at both places. But this is more like the latent space of this generator, which takes in an image. But that image could also be considered the latent in the particular case of generating from completely random noise. So I hope that kind of clears it up a little bit. That at least explains why it's right at the end in this diagram, because when we want to generate when we want to generate a new image with a diffusion model, we feed in a completely random image. And so that's our like random input, and it's going to go out and produce some output after a number of steps. Okay, I hope that clears it up. There's another question. How do RNNs and CNNs fit into the diagram above? Flow-based models are grouped together with VAEs. How are they different? So CNNs, okay, convolutional neural networks. This is like a general structure. And so, for example, in a lot of GANs, the generator and or the discriminator might be based on these convolutional style networks. But in and of themselves, they aren't necessarily able to generate anything unless you set them up in the right sort of way. So those are kind of more like the actual implementations of these. And so you could implement a GAN using convolutional neural networks or some other architecture. As for recurrent neural networks, they sort of in a different class of like sequence models. So they don't quite fit into the same strategy. But you can, I guess they're different in that also a sequence model outputs the probabilities of the next token usually, and you can randomly sample from that. So your Z might be considered how you sample from these kind of probabilistic sequence models like a recurrent neural network or a transformer. But yeah, this is by no means like a comprehensive overview. It's just a few of the large sort of types of models and classes. And the reason it's not talking about specifics like convolutional neural networks is that a lot of these blocks can be built from different ones. As for VAEs versus flow-based models, they both have a very similar idea. We take an input, we encode it into some smaller representation, and we decode it back. And the idea is that in the best case scenario, this learns to compress images really effectively, and we get images out that look very much like the images in. And as a bonus, if we pick a random latent variable, we get a plausible image out. The only difference between a VAE and a flow-based model is that in a VAE, the encoder and the decoder are kind of separate. They can be different architectures if you like. They can be different sizes, often slightly different numbers of parameters, and they're learned separately. I mean, they're learned together in the same process, but they're completely separate sets of weights, and there's nothing to guarantee that the decoded version is going to be exactly the same as the encoded version. In flow-based models, what they do is they say, okay, whatever our operation is that encodes this image, we're going to do the exact mathematical inverse of that operation to decode it, right? And so now instead of this being a bunch of weights that we learn and this being a bunch of weights that we learn, we can have the encoder be defined by some parameters still, but they're going to also determine the decoder, right? So this flow and inverse are going to be sort of mathematical exact inversions of each other. And so that has some mathematical advantages, but there's a place for both. And so, yeah, they both kind of get used. I think at the moment, at least I seem to see more variational autoencoders just because it's easy enough to learn the encoder and decoder separately. Okay, managing screens, back to Twitch, some more stuff. Okay, name of clip models and klube models. I sort of saw that question, but I chose not to see it because I'm not entirely sure. There's some schema to the nomenclature about exactly how large networks are, how large of an image patch they're taking in. So I think the /32 or /16, those are when we look at something like I'm trying to think if I've got a good example open anywhere. I guess we could look at this because it talks about here tokenizing our image into these patches. Each of these patches might be like 32 by 32 pixels. And so the size of those patches, I'm not exactly sure how is related to the number after the slash in some of those clip models. But yeah, I can't off the top of my head give you a good explanation. But the klube ones follow the clip convention. And the one that I showed there is, I think, currently the one that seems to be doing the best at various benchmarks. So I don't worry too much about it. I really should go and look up what the L and the H mean. But I can try and get back to you on Discord if you can't find that anywhere. I know who to ask. Great. All right. Well, that's about it from the stuff that I had planned. So I reckon we can now say, if anyone's keen, put a little message or a thumbs up in the Lesson 7 Discord, and then we can jump onto the voice chat in the lounge. If you don't have the GitHub link, if you're just watching the Twitch stream, let me just quickly drop the current sort of Discord invite in the Twitch chat. And then we can go and hang out there if anyone's got any further questions. There we go. I've dropped that in the Twitch chat. Oh, you can probably see it on the screen as well. I'm going to end the stream here, and we'll see you in Discord for future follow-ons.